Okay, everybody, we're going to get underway here. So, plan tonight is we're going to finish up some ideas within chapter 4 and begin content from chapter 5. I put the symbolism here because chapter 4 we're looking at aqueous solutions, so that's all about water. In chapter 5, when we move on to aspects of energy and thermochemistry, I associate that with fire. So it led me to some of these alchemy related symbols of fire, air, earth, and water, because at least tonight we're going to hit 2 of those. The plan to wrap up chapter 4, we had a lot of, I'd say, specific ideas pertaining to solubility and precipitation, specific ideas pertaining to acid-base neutralization reactions, and then the third type, which were our redox reactions. We finished the chapter by adding some numbers to that, looking at the concentration of solutions and seeing how we can have solution stoichiometry, do calculations involving that. We looked last time a little bit to get started on this idea of looking at concentration. That was in section 4.5. 4 different sections within that, or subsections, when we're looking at molarity. How do we express the concentration? Do conversions involving molarity, moles, and volume. And an idea we didn't get to last time, which is on dilution. So when we're looking at concentration, there's different units you can use. This semester, the only one we're going to use is molarity, moles of solute per liter of solution. So we looked a little bit about how you might make a solution like that. If you use volumetric glassware, you know when you fill it up to the line on those, that solution has a particular volume. When I was looking at this to do some calculations, I find that the key step for me right from the start is I have to ask, well, how is the electrolyte dissociating? Because I can't talk about the solute that I have there until I first figure out, well, what's in the beaker? And I do that by first of all thinking, well, how is it going to dissociate? And from there, I can now express the amount of solute that I have. Maybe I need to figure out how many moles of chloride, or in this case, it was for the entire solution, the sodium chloride aqueous, and then that would be in half a liter. And that would be then the molarity for that solution. We looked at another example, an application of that. In this case, and again, I would start by saying, how does the strong electrolyte dissociate? So I can then figure out how many moles I have of the particles in solution as it dissociates. And I can then express that in terms of the solute, the moles. In this case, it was asking about the sodium ions. In the 2 liters, that would be then the molarity for the sodium plus. I come back to, I think that a key step within here, before I start doing anything with the math, I have to pause and say, how does it dissociate? It comes back to the first part of chapter 4, asking, what's in the beaker? This is where we are then wrapping up. We had 2 sets of questions. The first one was in 4.69a, looking at the highest concentration for potassium ion. And we had 3 different solutions. You notice there's different molarities. We can't just look at the molarity all by itself because they dissociate and give me potassium ions in different ways. KCl will give me 1 potassium ion per formula unit. The potassium phosphate gives me 3. So I need to combine how the initial concentration is with how it then dissociates. So for KCl, the concentration from the potassium is the same as the concentration of the initial solution. For the potassium phosphate, I end up tripling it. That's where we are looking strictly in terms of the concentration. Now let's add a new idea. So within B here, we're talking about the number of moles that we actually had. Concentration, that's a description of the solution. The number of moles, well, we need to be able to get to the number of moles because, as we know from chapter 3, that's what's important when we're looking at solution stoichiometry. So this one right here, looking at the number of moles that we have in these different solutions. If we go back to the definition of molarity, that's moles per liter. And we find that if we do then the concentration in moles per liter times the number of liters that we have, that will get me to the number of moles. The solution information of molarity and volume gets me to the number of moles. This right here, really important relationship. I don't think this gets a big enough description within chapter 4. For me, this is really important. because we know that when we're doing chemical reactions, we're about moles reacting with moles. This shows me how I can use solution information, concentration and volume, moles per liter and liter to get to the number of moles. So we're going to work through a couple examples where we use this. I think it's a really important relationship for us. So for answering part B here, and we're asked how many moles do we have, I'm going to first of all look to see, well, I see how it can dissociate. I can see that K2CrO4 ionic compound will give me 2 potassiums. The potassium phosphate will give me 3. So if I know how many moles I'm starting with, I won't be able to determine how many moles I end up with. So I'm going to ask you to calculate something for me in just a second. This is how I would set up for the first one. How many moles am I starting with? Well, I have solution information. It tells me that I have 30 milliliters of a 0.15 molar solution. I'm going to be combining the molarity with how many liters that is to get to the number of moles. In chapter 4 here, being able to convert between milliliters and liters, moving the decimal point 3 times, we're going to end up using that quite often. So moles per liter times number of liters I have gets me to the number of moles. Then if I look how that dissociates, it dissociates 2 potassiums for every 1 of the K2CrO4. So this would tell me how many moles then of potassium I have in solution when I add the K2CrO4 as the solute. What I'd like you to do right now, see if you can write down, how would you set it up to solve for how many moles of potassium you have when you're using the potassium phosphate? You've got solution information right there. Take a second, see if you can set that one up. So in order to answer part B there, if we want to know how many moles of potassium is present in that solution, we have to consider how it dissociates, and we have to use the solution information to figure out, well, how many moles am I initially starting with? Solution information, again, is concentration and volume. Moles per liter times the number of liters we have will tell me how many moles I have of the initial potassium phosphate. And then how much of the phosphate do I get from, the potassium I get from that? I triple it because that's how it dissociates. This idea right here, I think it's getting us now being able to figure out how many moles do we have in a given solution. Now, this would be looking at either the concentration or the number of moles. Sometimes we change the concentration, and we do that by doing a dilution. So within here, here's an image from the book where it's describing what takes place during a dilution. A lot of times within these, we have particular volumetric glassware we're using, things like volumetric flasks, pipettes, and we have like a scenario describing what's going on. So to track through what's going on within this picture right here, it says that you're starting out with this really deep blue solution. It's a 1 molar solution. A certain amount of it is being transferred with a pipette. A pipette is going to transfer precisely 25 milliliters. It's being placed into another volumetric flask. And then after you add the water up to the line, you now know what that total volume is. Notice how the color has gotten lighter because it is not as concentrated. You've diluted it by transferring in a certain amount of that solution and then adding more water to it. Now, when we're doing a dilution within here, here's an equation that we want to use for that. What we're doing within here is that we have a certain number of moles of solute that we initially have in the first solution. Those same number of moles are being transferred when I use the pipette into the second one, but the concentration changes because I've then add more water to it. So this idea here of the molarity in the volume of one solution is going to equal the molarity in the volume after the dilution. Sometimes you also see the subscripts M1V1 equals M2V2. This is going to be, anytime I see a dilution, and we're going to try to practice this in just a second, this is the expression that I'm going to be using. I have information about what I initially have, and I have information after I've transferred it and diluted it. So in this case right here, when I say I have information, I initially was transferring a 1 molar solution in that 25 ml pipette. When I transfer it to the new container, it's going to have a volume of 250 milliliters, and I'm going to solve then for what its molarity is. One comment within here, when we're looking at the volume, you could take the time to convert both of them to liters and then back again, but as long as the units are the same on each side, then it works out fine. You don't have to convert them to liters and liters. So as long as the units are the same in terms of milliliters and milliliters, it'll work out fine. Now, when I say recognizing a problem within this one, here's 2 examples of it. So it says you have a stock solution of 14.8 molar ammonia. How many milliliters of this solution would you dilute to make 1,000 mils of 0.250 molar? So as I'm looking at this, as soon as I'm seeing this idea where it says dilute, this equation's popping into my head. I have information about what the solution is initially for its concentration, and I have information about how it's going to end up. So I've got 3 out of 4 terms. In order to use this expression, we're going to have 3 out of 4 terms and solve for the missing one. The missing term here is how much I would have to transfer over in order to dilute it to make that solution. 3 out of 4 terms. The second example right here, part B, it's talking about the same stock solution. So in this case, I know the volume that I'm going to use. I know its initial concentration. I know the final volume, and it's asking about what would be the final concentration. I've got 3 out of 4 once again. I know that I'm using this 14.8 molar solution. I'm transferring 10 milliliters. I'm wondering, well, what would be the final concentration if after I transfer it, I fill it up to the line and I got 500 mils? So anytime I see a question pertaining to dilutions, I'm thinking this equation right here. M1V1 equals M2V2. The idea here, as far as Jasmine, to the conversions between milliliters and liters, if it's the same on both sides, you could take it and you could prove it to yourself if you want. You could take each of these and convert these into how many liters that you have. The molarity is still going to be the same. When we look at it as far as how the units end up canceling, it's going to be the same in either case. So in my example, I just keep it simple. I just make it so I have the same, whether it's milliliters on both sides or liters on both sides, it works out. Here's one that's related the same way, where I think that we're also thinking about changing the concentration. This is, or determining what the concentration is. This one says indicate the concentration of each ion when you mix together these solutions. So first thought is, we're not seeing a chemical reaction take place here. We're just taking one beaker of one solution, one beaker of another, and we add them together. So in this case, we're not seeing a reaction, we're just seeing how they mix. So as I'm looking at these, in each of these cases, it's asking me, what are the ions present in the solution? And if I want to know the concentration, I need to know what the final volume is. So in these examples here, they typically will say the volumes are additive. So if I look at this first one right here in A, what's the total volume going to be? It's going to be 42 mils plus 37.6 mils. That will be the total volume of the solution. What ions do I expect in there? I expect that the sodium hydroxide will give me sodium ions and hydroxide. I think, oh, I'm combining it with also sodium hydroxide. More sodium, more hydroxide. So the sodium is coming from both of those solutes, and the hydroxide is coming from both of those solutes. In each of the cases, if I want to know concentration, I need to know moles and liters. How can I get moles? Well, if I look at it, oh, I'm back to having solution information. Molarity and volume can get me number of moles. And that's true for all of these examples. I'm going to leave this one with you as a suggested problem. I'm not going to work it through, but this is a suggested one from the book. Give this one a try or mark it, 4.72. This is another thing besides making our solution and diluting it, we can mix two of them together. And again, let's be careful in this case. Let's try to describe all the ions that are present and see how the volumes get combined. So in this idea here of working with the solutions, I spent a little bit of time describing how we might be able to prepare them and do dilutions and quantify the concentration and the actual number of moles of the solute that we had in each of those solutions. That's going to connect with the last idea in the chapter, which is solution stoichiometry. So if I look at all the stuff that we've done in chapter 4, a lot of chemistry here. And this idea of titrations comes right at the end. Many times they're going to be examples of neutralization reactions. And the concentration of the solutions that we're using, that's going to be important as well. Those meet in this category here of titrations. Now, when I look with historical data, how people do on content from chapter 4, titrations oftentimes are the most difficult part of the chapter. But I don't think they need to be the most difficult part. I understand why they are difficult, because a lot of times they're written as scenarios. They're sort of like a story problem. And as you know, it's easier if you already know the story. And sometimes a story problem in chemistry, it's confusing just to try to make sense. Well, what is the story that they're talking about? Students see numbers and they're unclear with how they fit with the actual scenario of what it's describing. And crucially, they oftentimes don't write a balanced equation. They see numbers and they say, I got to start using these somehow. And they don't take the time to write a balanced equation to start. They grab the numbers and they just start manipulating them in some way. I know that the best first step, you have to write a balanced equation every time. When I say that I've studied this, I've looked at the work that students have turned in before. And if the students wrote a balanced equation, their chances of success so much higher. If there wasn't a balanced equation written there, if they just started manipulating numbers, it was much less likely students would do well on these. So let's just make that our first plan. When we're trying to do solution stoichiometry, let's always first start with, well, what is the balanced equation? Because if we have a balanced equation, we can think about it like we did back in chapter 3. With chapter 3 with our stoichiometry, we looked at a lot of different ways that we could have reactants combined. Same thing here. Key step is all of those included a balanced equation. So let's make sure we have that when we're looking at them involving solutions. So first thought then is, let's sort of think about this back like we did in chapter 3. In chapter 3, when we first were looking at equations, first looking at reactions, we would make sure they're balanced. And if I look at this, this looks to be balanced. Second is we recognize that moles reacted with moles. So if I had a question like this, how many grams of sodium hydroxide are needed to completely react with 0.5 moles of hydrochloric acid? I got to make sure that moles are reacting with moles. Now, we looked at that a couple of different ways. If we were thinking about it in terms of a BCA table, we would say that we started out with 0.5 moles of hydrochloric acid. To neutralize it, that means we want to use all of that up. Now, if I look at the coefficients are 1 and 1. So if I want to use up 0.5 moles of hydrochloric acid, it's going to take 0.5 moles of sodium hydroxide. In a way, I'm just looking at this left-hand side of the BCA table, just to keep track of what I had. So in order to use up half a mole of HCl, I'm going to need half a mole of sodium hydroxide. Now, in chapter 3, How would I do that? The question here is in terms of how many grams. So I know that I need half a mole. I'm going to use the molar mass to figure out how many grams that I would need. Remember when we were getting into or out of the BCA table, we used the periodic table to look at the molar mass. That's all I'm doing right here. In chapter 3, we converted between moles and grams by using the periodic table to get to the molar mass. Now, maybe you're not a BCA table person, which is fine. Everything here is the same. I'm just showing you how you could set it up with dimensional analysis. In this case, you start with half a mole of HCl. I'm going to use the coefficients and see that they're 1-to-1. I'll use the molar mass of the sodium hydroxide, and that would allow me to figure out how many grams I need. So in this case right here, I'm starting out and I have half a mole of the HCl. I'm using the coefficients and it's 1-to-1. I'm using the molar mass, and that would lead me to how many grams that I would end up needing. Now, I want to switch it a little bit right here. The only thing that I'm going to switch, instead of saying we have a certain number of grams, let's look at it in terms of the solution information. Solution information, that's what we just talked about a moment ago. Solution information is concentration and volume. So this is exactly the same. We still are talking about half a mole of HCl that we're going to use up. We still are going to see that that's going to require half a mole of sodium hydroxide. The only difference that I have right here is instead of asking grams, we're asking about the solution. If you remember our solution information, we mentioned it just a second ago. Molarity is moles per liter. So if we have moles per liter and liters, we get to number of moles. If we have 2 out of 3 of these, we can get the missing term. If we have 2 out of 3 when it comes to concentration, volume, and number of moles, we can solve for the missing one. In this case right here, we've got 2 out of 3. We know the number of moles that is involved. The concentration was given, so the volume is the only missing term. We've got 2 out of 3 within the scenario. So if we pause for a second, before when we went between grams and moles, we used the periodic table. Now we're going to go between solution information and moles by using our expression of concentration times volume equals number of moles. That's all that we have to consider when we're now looking at this in chapter 4. That shouldn't make it that different, shouldn't make it that difficult. So within this one, if you're not a BCA table person again, this is how I would set it up. I would say in this case, I'm again dealing with half a mole of HCl. I'm going to use the coefficients and figure out that I need half a mole of sodium hydroxide. Once I get half a mole of sodium hydroxide, I go back to the exact same expression here. Concentration times volume equals number of moles. I've got 2 out of 3. I know the number of moles. It told me the concentration. The only missing term was the volume. That's why I think this expression right here, this equation, such a crucial part in chapter 4, because this allows me to go back and forth between the solution information and the number of moles. Let's work through this one as an example. So this one's sort of set up here as a scenario. In a titration, 15.52 mils of sodium hydroxide is needed to neutralize 20 mils of 0.225 molar nitric acid. What is the concentration of the base? So this is an acid-base reaction. Sodium hydroxide is the base. Nitric acid, HNO3, that's the acid. I have all the information about one of these. I have all the information about the nitric acid. It tells me the volume, it tells me the concentration. I've got all of the solution information I need. For the sodium hydroxide, I only have the volume. So let's see how they react together and figure out the amount that I would need of the sodium hydroxide to neutralize the nitric acid. So the very first step here is I got to make sure I got a balanced equation. Crucial first step. This looks to be balanced. Now, oftentimes when we're looking at these titrations, It's not asking me how much sodium nitrate forms. It's not asking me anything about the products. I'm just interested with how the reactants combine with each other. I've got all the information about the nitric acid. I can get to the number of moles of that because I've got concentration times volume to get me to the number of moles. Moles per liter times liter gets me the number of moles. So I know how much nitric acid I started out with. If we use either BCA table or dimensional analysis, exactly the same approach. I started out with a certain number of moles of nitric acid. I'm going to use it all up. I look at the coefficient, and that tells me how many moles of sodium hydroxide I would need. If you want to set it up here to follow it through, it's exactly the same thing. I have a certain number of moles of nitric acid. It reacts 1-to-1. This is how many moles of sodium hydroxide I would need. So now for the sodium hydroxide, I got 2 out of 3. And by 2 out of 3, I mean concentration, volume, and number of moles. I've got number of moles. I've got the volume. I'm solving for the concentration. I got 2 out of 3 within the set. So once again, whether we set it up with a BCA table, dimensional analysis, make the connection back with chapter 3. With chapter 3, we went back and forth between grams and number of moles. By using the molar mass, we looked up things on the periodic table. Now we're going back and forth with the solution information. You're going to hear me say it once again. Concentration times volume gets me to the number of moles. If I got 2 out of 3, I can solve for the missing 1. Never hurts to look and pause and say, okay, does this concentration make sense? Just as a quick check. Nitric acid and sodium hydroxide were reacting 1-to-1 in the balanced equation. I used a little bit more of the nitric acid than I did of the sodium hydroxide. So the only way they can match up, the sodium hydroxide must be a little bit higher in concentration. So that quick check at the end, yeah, that makes sense. Here's the book's outline. The book's outline, I think, is aligned with what I've been saying. We want to use the coefficients from the balanced equation and use the solution information to get the number of moles that's involved. Let's look at this one. Here's the sample exercise that's worked through. So as I read through this one, it's describing an acid-base reaction between sodium hydroxide and sulfuric acid, H2SO4. And it's asking for the concentration of the sodium hydroxide. So as I look at that one, what jumps out to me as I read it is, okay, I'm going to make sure that I have a balanced equation. And I know that it's not going to be 1-to-1 for the coefficients. The reason I know that is sodium hydroxide has 1 hydroxide, sulfuric acid has 2 protons that it can donate. So I got to be careful when I write a balanced equation for that. Here's that same setup, the same scenario, and here's the balanced equation. Crucially, we've got to have the balanced equation. Now, I'm going to work this through and see how we could either use a BCA table or the work through example in the book. I think exactly the same ideas are involved. So within here, I have all of the information about the sulfuric acid. I know the concentration and volume. With concentration and volume, we can get number of moles. Now, I know how much sulfuric acid I'm starting with. I'm going to use it all up. Now, this is the part I know we have to be careful with. Look at the coefficients. 1 for the sulfuric acid, 2 for the sodium hydroxide. So I need to make sure that I have 2 sodium hydroxide for every 1 of the sulfuric acid. If you set it up with the dimensional analysis and you want to work it through, that's what the book describes here. It first determined the number of moles you had of the acid, and then it said, let's be really clear. We need to figure out and use the coefficients in the balanced equation. Now, in both of these cases, it's led me to how many moles I would need of the sodium hydroxide. With the sodium hydroxide, we're back to having 2 out of 3. We know the number of moles, we know the volume, so we can solve for the missing part, which is the concentration. This shouldn't seem that different from what we were working on in chapter 3. Once again, we're using the coefficients in the balanced equation. The only feature that we've added to it, once again, is instead of using the periodic table, we're using the solution information where we have concentration and volume. Now, sometimes within here, students say, okay, Clark, I get what you're saying, but I can do this more quickly if I use the equation M1V1 equals M2V2. Can I use that for a titration? So help me out within here. I'm curious. Tell me in the chat. Do you use this for titrations? Were you told to use this? Is this your general strategy? So most the initial responses I have coming in say, no, that wasn't how you used it. Excellent. Okay. Because I have a lot of folks that when they enter this class from high school, they said, yeah, my high school teacher said I should use this for dilutions. Excuse me, I should use it for titrations. I think that I would only use this for dilutions. When I say I've researched this, I've seen what students do within this one. M1V1 equals M2V2. I think let's just reserve that for using it for dilutions. Sometimes students say, well, this seems like sort of a shortcut because I can just plug in these for a titration. That idea of just plugging it in, that only works when they're balanced and it's 1-to-1. I mean, you can adjust it, but I think if we just think about titrations as stoichiometry problems, we don't even have to bother with that. When I've seen how students solve these, I've seen that the students have absolutely the best luck, the best success rate when they treat a solution stoichiometry problem, when they treat a titration, just like they would other aspects of chapter 3. And that the only variable that they change within here is, once again, instead of using the periodic table, they're using concentration times volume to get to the number of moles. Now, I've said several times within here that the first step has to be writing a balanced equation. Here's 2 practice exercises that I grabbed from the book. So first of all, let's recognize how these are both titration questions. So this practice exercise, what is the molarity of an HCl solution if 27.3 mils of it neutralizes 134.5 mils of barium hydroxide? Okay, this looks like an acid-base neutralization reaction. I have all of the information about the base. All of the information because I have its volume within the, oh, wait 1 second within here. Maybe, wait, let me correct what I'm saying right here. I think within this one, I don't think I have all that information. I think within the second case, practice exercise 2, I do think I have all the information. Practice exercise 2, I think I have both the volume and the concentration. In this first one right here, I'm going to write an oops next to that. I think I put this one in here because I recall students asking me questions about this one. Because within this one, it looks like you don't have all the information. In order to do the solution stoichiometry, you need a balanced equation and you need to know all the information about one of the solutions. I think you have that in practice exercise 2. I think something's lacking here within practice exercise 1. Take a second though for both of these. I've mentioned that anytime we have one of these, the most important thing is our very first step of writing a balanced equation. Take a second, see if you can put that into practice. Write balanced equations for both of these, please. Both of these are acid-base neutralization reactions. Take a second, write balanced equations for both. Both of these cases, I see an acid reacting with a base. I'm expecting that it's going to form water. And I'm going to have the leftover ions are going to form an aqueous salt. These would be my balanced equations for it. I see that the barium hydroxide has 2 hydroxides. So I end up having 2 HCl's within that balanced equation. And here's the example down below for the sodium hydroxide. My strategy when I'm solving these, when I'm balancing these, I look and I write what the salt is first, personally. I write what the salt is first, and that helps me then look back to balance the reactants. Now, my last thought within here, when it comes to our titrations within this, I've said several times, it's really beneficial to write the balanced equation. Whatever your strategy, whatever your problem solving is, I know you're going to have better luck if you write that so it's staring you in the face right at the start of the problem. So within this whole group right here, we've practiced a couple titration examples. We also looked a little bit at solutions and dilutions. When I look back here within chapter 4, whether the progression through the ideas, or if I look as far as sort of the degree of difficulty here, I'm really confident that your next test is going to have questions in all of these different categories. So I would say right now is a great time to consolidate your understanding of this. A great time to summarize your understanding for all of these different topics. We're going to be moving on to different ideas beginning tonight as we move on to chapters 5 and 6. We're not going to return to really practice these in chapter 5. We're not going to really return to practice these in chapter 6. They're sort of standalone ideas for us. So please try to master them right now. Try to overlearn the ideas the best that you can. If you can recognize something as a dilution, have a plan and a strategy and execute it. If you recognize something as a titration, have a plan, have a strategy and execute it. Same thing with using the activity series. Same thing with using solubility rules. Now's the time this week, I would say, to try to bring together your understanding for chapter 4. Now, let me point out a couple things as far as resources that I have available right now that you might find helpful. Before I mention these, let me just say, I think people are doing a really good job in perusal leading into class. I think what you're going to find is that's going to become an even more important idea for us, an even more important resource for us. Because what I was seeing within perusal, people had the time to write down, show their work through different calculations, share ideas. I know that we've got a lot of content coming up in front of us with chapter 4, 5, and 6, and for the rest of the semester. So let's try to maximize our learning asynchronously there with perusal. Keep that up. I'm really impressed with the contributions folks are making. As far as a few optional ones that I've added, I've put together, your choice if you're going to find this helpful or not. Some students do, some students don't. So I mentioned last time this program that would allow you to sort of test your essential skills. This essential skills program, I give the link right there, essentialskills.osu.edu. It's free to use. This week, I've loaded it up with some questions involving oxidation numbers with Monday, redox reactions, activity series, looking at acids and bases and electrolytes. And in each of these, they're just a really quick check-in to see if you know the idea, if you can apply it. Answer 3 in a row correctly, you're done with that particular topic. If you want to just sort of put this in as something that you want to just revisit real quickly, at lunchtime, I don't know, whenever you're feeling like you need it to explore your essential chemistry skills, whenever that happens to be, this might be a resource for you. I'm going to keep populating it. If you find it helpful, great. If you don't worry about it. It's at essentialskills.osu.edu. Second resource that you might find helpful is I reached out to some students that I know were successful in general chemistry. Some of them are in the second semester right now. Some of them are in organic chemistry. They've moved on. They're all people that I know are quality individuals. I think in some cases, a peer like that they might be able to help you in this class in ways that I can't. They know more about what does it mean to be a student than I do. Okay. I mean, I try to imagine what your world is like, but I don't know. So I've asked them to reach out to some students within this class, learn from you a little bit, and see if we can help you as the course is going forward. So let me send you a quick polling question. Tell me, do you think you would like to be contacted in this way? You certainly don't have to. Do you think it would be beneficial to have someone who's sort of a veteran of the course reach out to you? Picking up a couple questions here that came in into the chat. Provided information on the test includes the solubility guidelines and also the activity series. Dan's question as far as the essential skills one, I can't really reset or change any deadlines in that. Don't stress if something is come and gone. There's going to be just daily ones going forward. So I'd say use it going forward if you think you might want to try it. Don't worry at all about things that have already passed in that. So what I'm going to do with this information right here, I'm going to begin with the folks that are most enthusiastic, saying you think that this would be beneficial, and then I'm going to have my team try to contact you. That will take place over the next week or so. Okay, next question for you. I've spoken with some students within this class right now, and it seems like in that strange Zoom world we're in, it's difficult sometimes to work with classmates. I mean, before we'd all be in an auditorium and you could just look at the person next to you, turn to the person next to you. People sit in the same seats all the time, and it'd be easy to network and form study groups and stuff like that. I'm beginning to learn that that's not an option the same way, because after all, I mean, people are sitting in the rooms all the time. So how about this one? I think that I can help people within this class network and contact each other. I can just share emails in a way that you might not be able to do. So how about this part? Do you think this is something that you would be interested in? Do you want me to play matchmaker here and start to help get some contact information for students so you can begin to share ideas? And once again, within your response here, if you're in the category of you think this would be very beneficial, you're going to be my top priority, and I'm going to try to make that happen. It occurs to me there's probably, I don't know how it escaped me. Seems like there's some corny joke I should have had in place about chemistry of some kind. I don't know. There's a joke in there somewhere. I don't know why I let that one fall through the cracks. So I'm going to, within this one, I'm going to see if I can help people out with that. Last thought within here is I made a video and I put it in Perusal where I give sort of an overview of the first exam. And by the overview, I picked about 2 or 3 questions that I know are ones that were the most difficult. We can't release the entire exam to people because the data set that it draws from, the question bank, we reuse those questions in different ways. They're found in different exams, they're found in the makeup exam, sometimes they're found on the final exam, different things like that. So I can't just release the entire exam. So I thought I would do the next best thing. I took some of the content that I'm comfortable with sharing and I put it in this very short Perusal video. If you think that that is something that you might want to look at, just check it out within Perusal, okay? It's like a 12-minute video. I talk about the first test. I talk about some of the questions that were lower scoring. I give a couple suggestions as far as how I would use that information going forward. I know some of you are reaching out to me about trying to learn from the test in some ways. Start with this, okay? Start with this, and if we need to then explore or think about things or make a plan going forward, I'll be happy to. But I think within this video that I put in perusal, and I just listed that there's optional showing up tomorrow. That's my best first effort to try to help you understand how you could perhaps learn from the exam that we just had. Now, with that, I want to move on to some ideas to get started within chapter 5. So within chapter 5, when I put it under the heading of fire, well, we're looking here about the this idea of energy. One thing before we move on to this one, I noticed within the chat, there was a question about being able to see the test during office hours or something. I can't disclose the test really in any setting, okay? The most that I could disclose it is what I already put in my video, okay? I can't distribute the content in any other way. If you're curious about particular ones, I could look specifically at your test myself and try to summarize it in some ways, but I can't be sharing the content any more directly than I already am within that video, okay? So as we move here within chapter 5, we're going to get a start right here at the very start of it. We're going to get beginning here right at the very start of the chapter. And we're going to look a little bit, what do we mean when we're talking about energy? And we're going to see that we have sort of a lot of different terms or definitions that I want to spend time so that we understand what they are. And then most of the rest of the chapter, we just run through to see how these ideas then get applied. So this first one, I think, really important because it's seeing the different concepts. Some of these are terms that I know when I saw within perusal, they're things that you've seen before, but I want to try to take it and show you how it applies in a chemistry class. So this is what we're going to be trying to make sense of. Concepts of heat and work. The symbols for that are Q and W. Two different kinds of energy, potential energy and kinetic energy. We've already been talking about those a little bit. A new one for us, which is called the internal energy, and also the temperature. We've seen some of these already, but now in chapter 5, we spend time and we look more specifically at how these ideas fit together. So first of all, let's be aware that energy is involved in chemical reactions. Here's a picture of me when I'm in my lecture space, my big auditorium, exploding a hydrogen oxygen balloon. The unit of energy that we're going to use is called the joule. And a lot of times the units, instead of joules, we look at them in kilojoules. So I'd say, which are thousands joules, right? So we're going to see our units are typically going to be joules or kilojoules. Within the pre-class video, we looked at this relationship between kinetic energy and potential energy. We looked at that by seeing that skater who is going back and forth on a frictionless track. And we saw that there was a trade-off between the kinetic energy and the potential energy. The total energy stayed the same, but when he paused way at the top right here, his kinetic energy went down to 0, and he had the largest potential energy. In this case, he was going back and forth because gravity was pulling him downward. As he was pulled downward, the potential energy decreased and the kinetic energy went up. And he had a maximum kinetic energy when he was right at the bottom as he was zipping through, back and forth. So as we begin to think about this and where it fits with chemistry, here's one important idea for us. The potential energy goes down and is the lowest when the particles of matter are attracted to each other and they are close together. When there's an attraction and the particles are closest together, the potential energy goes down. So right now, let's just think about it in terms of gravity. Look at a table that's right next to you, okay? Where maybe you got something sitting on the table. Maybe it's a pencil, maybe it's, I don't know, a book. It's sitting on the table right now. I think it has the potential to fall to the floor and gravity can pull it there. If you knock it off the table and it's now resting on the floor, it doesn't have that potential anymore. The potential energy has gone down. If you did that same thing, but instead of being on the table, let's say it's on the ladder, it has even greater potential energy. But once it comes together, the potential energy is decreased. Now, what does it mean to say the potential energy has decreased? Crucially, it's going to be relative to what we are calling zero potential energy. Depending on what we set our potential energy reference at, you could have a negative potential energy. That's not like spooky or sci-fi or something. It all comes back to what are we calling zero potential energy? So if you had your person on a skateboard ramp going back and forth, if you call your zero value right at the bottom, you could see that when the skateboarder is at that position, it would be zero potential energy. If the skateboarder is going back and forth in exactly the same motion, but you called this top position zero potential energy for your reference, now when the potential energy gets smaller, it becomes negative. There's nothing spooky about negative potential energy. It's all relative to what we are calling our zero position. And in chemistry, we are going to call our zero potential energy reference point when the particles of matter are far apart from each other. Here's an image that we have within the textbook. Let's talk through the details here and see if we can understand it. So what we see right here is it's defining zero potential energy. That's what this zero means here. As the particles of matter move far apart. As the particles of matter are attracted to each other and come closer together, the potential energy will go down. So that's what it's showing on this bottom part of the picture. It's saying that you have two different charges. One is positive and one is negative. As those charges come closer together, the potential energy is getting smaller. And because we defined zero as being when they're far apart, the potential energy is becoming more and more negative. What I'd like you to do right now, let's do a little demonstration. Okay, I usually do this in a classroom with 300 people. I'm going to assume that you're playing along with me, okay? What I want you, and I'm going to be doing it right now too. What I want us to do is in each hand, put a magnet, okay? Have two fists, put a magnet in each hand, okay? Have your hands be far apart from each other. I'm doing it. I want you doing the same thing. You have two clenched fists, each with a magnet that are far apart from each other. Now, as they start to come closer together, so move your hands a little bit closer together, a little bit closer together. Mine are about 8 inches apart. They're getting closer together. And now I'm starting to feel a tug between them. And now I'm feeling them pull all the way together. They're all the way together. The potential energy now is at the smallest. They're attracted to each other and they've moved all the way together. I'm going to now try to pull them apart and okay, they're back apart. They're back to having zero potential energy because I had them fall far apart. As I feel them come closer together as they're attracted, okay, now they're all back together. Negative potential energy. Okay, now I'm curious within here because I've seen this when I do it in person. Tell me in the chat, did you play along with me? Yes or no? I like the comment, of course. Of course, you got to play along with me on this one. Okay, I think it's a good move. Okay, now this idea of what we are calling zero for a large separation, that's our reference that we are choosing. When we're talking about potential energy, it's all about the position and the fact that our particles can either attract each other or repel each other. When we are looking at this one, the force of attraction or repulsion that we have is due to the charges. We're looking at the electric potential energy. The particles of matter that we have as chemists, they're too small for gravity to be important. Gravity depends on the mass, the size of the particles. Our particles are too small. As a chemist, we are going to be talking about the attractions and repulsions, and it all has to do with the charges. We've already seen how we have charges when we looked at cations and anions, for example. Here's an equation that describes how the charges are important. I want us to be in this space right here. And what I mean by this space, so much of our discussion is going to be the particles of matter are attracted to each other, and as they move together, the potential energy goes down. Now, we can do the same thing right here and think about it in the opposite way, okay? Now, in this one, I don't want you to dislocate your shoulder, but if you had two magnets, okay, and you know if you flip them over, then instead of attracting, they're repelling. So take your two magnets in your two clenched fists and take one of them and turn it over so it's pointed in the opposite direction now. They're still far apart, but now there's a repulsion between these. As you bring them together, it's tough to bring them together. As you try to bring it together, they now have the potential to move apart from each other. They're not sticking together, they're pushing each other further apart. This would happen if the two charges were the same. As you try to bring the charges, if they're both positive or both negative, if those get closer together, the potential energy is going up. If you squeeze those together, they now have the potential to move far apart. They go back to where they started from. This idea conceptually of when repulsions occur, initially it's not going to be that important for us. We're not going to do math with the idea here, and we're really not going to do much with repulsions. We are going to do a lot with attractions. So in some ways, we're interested in when the particles are very far apart and the potential energy we call zero, or when they start to move closer together, they get a lower potential energy and it becomes more negative. This is the space that we're going to be at so many times as chemists. Now, let's start to take this and connect this now to some chemistry, because we have the skate park, fine. I've talked a little bit about potential energy, fine. How does this now start to fit together with some chemistry? So let's say we think about it this way. Let's say we've got two ions that are stuck together, a cation and an anion, like maybe sodium ion and chloride ion. So let's say these two ions now are stuck together. Where would you place the potential energy on this scale? Do you think the potential energy would be at position A, B, C, D, or E? I'm going to shoot you that as a polling question. The cation and the anion have come together. Where do you place them on this? So as this is coming in, really interesting. Our poll is about 50-50 between two choices. And they would be the two choices that I would have anticipated. Now, before I show the poll within here, I want you to come up with an explanation. Think for yourself. Why did you make your choice? Don't tell me it right now, but come up with like within a sentence or so. What is your explanation for your choice? I don't want to put words in your mouth, so I'm just curious, what would you be thinking for your justification? Okay, now, sorry about that. Now, let me share the results with you. We're about half and half between people saying they think that this should be described as zero potential energy, and others say that it should be no at position A, it should be very negative. About half and half within that. So I'll tell you what, if you're someone that said it should be zero, tell me in the chat, convince me. Why should it be called zero potential energy? Okay, so a couple folks within here are describing the previous equation that we had. Let me show you how the equation fits into this expression right here. I'm going to try to convince you that the best answer is A, that when these have come together, they're very close together, that is a very negative value for the potential energy. If we go back to our expression right here, one of the charges is positive, that's what, and the other charge is negative. That's what the Q values are. So one of these is positive, one is negative, so the overall sign is going to be negative. The distance has gotten smaller and smaller and smaller, so that makes the entire value larger and larger and larger. You've got a smaller and smaller number in the denominator, the whole term then gets larger and larger. Because one of the Q's is positive and the other is negative, it becomes a greater and greater negative number. So even though you don't have to do the math, that's where the math part is coming from. I think the best answer is they've come closer and closer together. The potential energy has decreased. And since we're defining a very large separation as zero, they've moved on my number line here more and more negative. That's what's shown in this image right here. If you have the ions, and here I show a lot of positives and negatives, if they're all spread apart, the potential energy is higher than if they all come together. As they're coming together, the potential energy is going down. And because we define our reference here as a large separation, it's becoming more and more negative. It's all coming back to where we're defining our reference value. This idea of as it's coming together, the potential energy is going down. I try to connect this back to the skater, where his potential energy went down, it became smaller, and if we are defining a reference as a large separation, it became more and more negative. Now, this idea of just like our magnets, when the particles of matter are stuck together, as they move together, that's a lower potential energy. It's going to take now energy to try to pull them apart. It's like our magnets. When our magnets are stuck together, it takes energy to increase their potential energy and move them apart. Anytime something is stuck together there, it's going to take energy to pull them apart. So what we're going to find here, as we connect this to other ideas in chemistry, it's always going to take energy to break a bond. The atoms are stuck together at a low potential energy when they are bonded together. It always takes energy to break a bond. Forming a bond is the opposite. Forming a bond will always release energy. This right here, really important idea that I think sometimes there's different misconceptions around. And you're not alone on that one. This idea that breaking a bond gives you energy of some kind, I'm curious. Have you ever heard that? Have you ever heard that breaking a bond is going to give you energy? Is that something that you've heard of and you agree with? You've heard of, you disagree with, or you haven't heard that? Quite a few students in the class have heard that before. A lot of times that is language you might hear in a biology class. I'll just say it straight out. If a biology teacher tells you that when you break a bond, you get energy, they are wrong. That is not what's happening. Okay, I'm not looking to get in fist fights with a biology teacher, but they're not telling you exactly what's going on. We'll look at that more next time within chapter 5. Let's now have this understanding. It always is going to take energy to break the bond. And forming it will always release energy. It's going to be an idea we come back to several times here in chapter 5. Now, when we talk about energy coming or going, within the video, we saw that there were different kinds of systems that we would be interested in. We're interested in the interplay of energy as it comes and goes between the system, the thing that we're looking at, and the surroundings, which is everything else around it. So here were a few different kinds of systems. With an open system, the energy and the matter could come and go between the system and the surroundings. We could make it where it was all sealed up and both the particles of matter and the energy stayed inside, or we had this closed one. So this isolated one, this is an approximation, okay? Like a thermos of some kind. As long as it can stay all sealed up and it keeps the same things at the same temperature, we might approximate that as an isolated system. If we look at the closed one here, the example they give is a piston. The particles are stuck on the inside, but we'll see in just a second why they are choosing a piston, okay? Why they are choosing a piston. We're going to do that when we look at a few ideas here in section 5.2. So first of all, we've talked about the potential energy and the kinetic energy. So let's say you had a gas and the particles are all moving around, bouncing into each other in many, many different ways. If you were to add up all of the kinetic energy for all of those particles and all of the potential energy that you have, that's called the internal energy. The internal energy is adding up the energies of all the kinetic energy, all the potential energies for all of the particles that you have. We generally don't know that as a numerical value, because I mean, how would you calculate that? How do you pause it and do a calculation within that? So we generally don't know the internal energy, which is given symbol E, but we're interested in how it changes. What is the energy that it takes when we're comparing one internal energy and another? That's what the delta means. The change in the internal energy, when we do the math, we're interested in the final condition minus the initial. That leads to the change that we have. This idea of setting it up where we do the final minus the initial, we do that many times here in chapter 5. So let's look at this one involving the internal energy. Here I show O2 solid at 31 Kelvin, O2 gas at 194 Kelvin. I think that the solid here has the lower internal energy. I think it's at a lower temperature, which means its kinetic energy is smaller. And the particles of matter are all together. They are at a lower potential energy. I think that the O2 gas at 194, it's at a higher temperature, which means higher kinetic energy, and the particles are spread out. In order to go from the lower internal energy to the higher one, I would have to add energy to it. That would be a positive value, because when I do the final minus the initial, the change there would be positive. So that's one thing when we look at the conventions that we have here. When we're talking about the internal energy, when that is a positive value, it means I have added energy to the system. It's come from the surroundings, it's gone into the system. Now, when I say that I've added energy, we have two different ways that we can add energy, Q and W. We can change the internal energy due to Q and W. Do you remember what the symbols were? Q was heat, W is work. We can change the energy due to changes in the heat or changes involving the work. So Q is our symbol for heat. When Q is positive, we describe that as being endothermic. Heat is going into the system. from the surroundings. When Q is negative, we describe that as exothermic. Heat is going from the system into the surroundings. This back and forth between the system and the surroundings, that's what the sign is telling us. Positive means heat is going into the system. Negative means it's leaving the system going into the surroundings. When I do this explosion, kaboom, that's exothermic. Heat is leaving from that reaction going into the surroundings. If you want to remember explosions as being exothermic and negative sign, that might be helpful for you. Now, when we're thinking about the work, that's the other way that we can have a change in the internal energy. The work that we're interested in chapter 5 is what's called pressure volume work, or PV work. If you think within a physics class, we describe work as being force times distance. The way that connects with PV right here, the force is the pressure and the distance is how the volume changes. So it's actually the same kind of expression, but this is what we think of when we have the volume changing and it presses against the atmosphere. When we think about our sign here, work being positive means work is going into the system. When work is negative, that means work is going into the surroundings. When I look at these two right here, positive in both cases means energy is going into the system, whether it was heat or work. Negative in both cases means it is leaving. Now, students usually have a much better sense on this idea of heat. Let me help you out within the work. If the system's volume gets squished smaller, that means we are doing work on it. Work meaning the surroundings is squishing it smaller. If instead the volume of the system gets bigger, it's pushing against the surroundings, so it is doing work. So if you look at the system, look at its volume change. If the volume of the system is getting smaller, that means the work was positive and work is being done on the system. If the system's volume is getting bigger, that means the system is doing work. That's why we're talking about pistons in this chapter. Because remember, we said within this one, this was an example where the matter stayed inside, but the energy could change. The energy is changing in the form of a volume change, and that's one way that we can change the internal energy. Here's a figure from the textbook. This one shows how this can take place in a scenario involving a reaction. So it says, if we define the system as the reactants and products, what would be the sign of the work here? So it's showing here on the left, this setup. They put some hydrochloric acid in the bottom, and they're putting in some zinc solid. I'm going to pause for a second and say, oh, you know what they're doing right there? They are showing a redox reaction. Zinc was present on the activity series, and it can react with H plus to form H2 gas. That was part of the activity series. If I form H2 gas, what's it going to do? It's going to push against this piston. So that's what they're showing within the reaction right here. They plopped in the zinc. It reacted with the H plus. Notice how that's a redox reaction. Zinc is going from an oxidation number of 0 to +2. The H plus, which came from the HCl, went from H plus down to 0. So I'd say the H plus was being reduced. Electrons were being added to it. It formed H2 gas, and it pushes against the piston now. So the volume of my system here has expanded. So take a second, think about this. What would you say the sign of work should be? Positive or negative? Key thing I'm looking for here, I'm seeing that there is a change in volume and the system is pushing against the atmosphere. It's doing pressure volume work on the surroundings. the work is negative. When the volume of the system increases, work is negative because it's pushing against the surroundings. So within this group right here, what do I want a few takeaways for us to be? So first of all, as we make sense of these different ones, we said that the internal energy is the sum of all of the kinetic energy and potential energy. And that's usually something that we find the difference of by considering the final minus the initial states. You can change the internal energy by either the heat or the work. Both of those can change the internal energy. When we are thinking changes involving the heat, that's when we use these terms endothermic and exothermic. When Q is positive, we're transferring heat to the system. When Q is negative, that's exothermic, that's like an explosion, kaboom. We are seeing we're transfer heat from the system to the surroundings. I show up here the different sign conventions. How do I see this on exams? Oftentimes I see scenarios like this. Let's look at this one. It says, let's consider water in a bottle. We'll consider that to be the system. We take that, we put it in the freezer. We find that the water turns to ice and the bottle breaks. My cat's joining us here. And the bottle breaks. For this process, assign Q and W for it. The system was the water in the bottle. Assign Q and W. I would say in this one, heat left the system when it went from being a liquid to the solid. That was an exothermic process. The system was cooling down. It was a negative sign for Q then. I think the system did work, however. It squished against it, it broke the container right there. The volume increased, so the work was negative. That's how I would assign those. How about this example right here? So here's one involving hydrogen and oxygen. Let's consider that balloon to be the system. If we are assigning our terms right there, I found this video. This one right here, this is not me, but this guy, as far as how he's handling it, what he's got written on his board, the class, this looks a lot like how I would run it. I would be wearing goggles, however, but let me show you what this looks like. Okay, so within that process right there, I would say that overall explosion was exothermic, okay? Don't be fooled by, oh, there was an initial candle that was brought next to it. The overall change that we had right there, it definitely released heat. It is definitely overall exothermic. And I see the volume increasing. So in this case, I think the work and the heat are both negative. So within this one, and I grabbed a picture of it. Here's when I've done the explosion myself, okay? It's definitely a fireball. It just goes right in front of your eyes, okay? I wore a little bit more of the gear than that guy did. But anyways, my point within this one, these were two examples where we looked at scenarios and assigned Q and W. I see that a lot of times on tests. Students do a lot better with the Q part than the W. But with the W, all we got to do is look for the change in volume. And that tells us our story on that one, okay? So as far as suggested problems from the start of chapter 5, I just have two examples right here. The main thing that I want to draw your attention to, and this is 5.4 and 5.28, is they're not about doing a lot of math within this section. They're more conceptual. We are going to do quite a bit with numbers in chapter 5. But right at the start, we're just trying to get a sense of what the ideas are. Next class, we're going to see the different kinds of things that we can do within our subsequent analysis. When we're going to be doing, I'd say, a big chunk of the chapter, Next time we'll probably do from about 5.3, maybe all the way up close to 5.7. I think we can get a lot of different ideas taken care of within that one. I think that the perusal setup for that one's going to be helpful. And I'll hang around and answer questions, folks. Once again, appreciate your attention. And I'll catch you next time.
Thank you, Dr. Clark. Have a good night.
Yep, thanks.